I'm following up on I'm sure great lectures you already heard about gravitational wave, and I have to warn you a little bit that I might have actually pitched my talk a little bit too pedagogical and at a very elementary level, and so you'll see, if I start actually explaining some trivial things or some duplicate things from the previous lectures, I apologize ahead of time. But anyway, so let me get started. My talk is basically about cosmology, as you heard from Kosaku, and one of the particular aspect of it is really about inflation. So let me sum up what I'm actually trying to tell you today. First thing I'm going to talk about is how you use actually telescope to look far, which means that you're actually looking back into the past. But there's a limit how much you can do this with electromagnetic wave, because eventually you hit the point that universe was so dense and hot that the photon can't propagate freely anymore. And that is the surface, which is called the last rescattering surface. So what we see in a cosmic microwave background is a photon that emanated from the surface. And so that's the limit, how far you can look back into the past by using electromagnetic waves. So here it says cosmic microwave background. This is the point when the universe was only 380,000 years old, as opposed to 14 billion years old as it is today. So this is really a baby universe. But my prime interest I'm going to talk about today is what happened before this point. And so in particular, the inflation is what happened at the very beginning of the universe. So in order to probe what was happening before this point of the last scattering surface, you need a different probe other than the electromagnetic waves. So the entire astrophysics astronomy had been based on the electromagnetic wave for many, many centuries. But now we have this additional tool, namely gravitational wave you already heard about. So the idea here is that using gravitational wave, we can get something from the very early moments of the universe, which comes straight to us. And that's a signal we would like to see, which you can never get using electromagnetic waves. So that's the basic message of how to use gravitational wave to probe physics at a very early universe. And that's basically the entire talk from me today and tomorrow is about. Okay, anyway, that's the basic message here. So before getting to it, so of course I have to first give you a review on the basic cosmology, because I don't think the cosmology has been talked about in previous lectures, am I correct? So I'm going to do a very pedagogical review on basic ideas in cosmology first, before get to the idea that you can use gravitational wave to probe the very early moments of the universe. So that's the plan today. So the first thing is that by using telescopes, you can look far away, which is the same thing as looking into the past. And we have various tools in studying the early universe. And one of them is using big telescopes. The Kosaku already mentioned Subaru telescope I'm a big user of now. And the particle accelerators, which basically reproduces what's happening in the early universe. And that's another subject of my intense interest. So these are the probes, are the tools we have to study the universe of the past. So for example, we actually built a new digital camera on the Subaru telescope a couple of years ago. And this is one of the first images we took of the Andromeda galaxy. And as many of you know, Andromeda is about 2 million light years away from us. But in the scheme of the entire universe, 2 million light years is only a very short distance, it turns out. It's just our neighbor, actually. And the Andromeda is so close to us that the Milky Way galaxy and Andromeda galaxy are actually pulling each other by gravitational pull. And eventually, in probably a few billion years, we're going to actually collide and eventually merge with the Andromeda galaxy. So it's actually so close in the scheme of the universe. But the point here is that because the Andromeda is 2.3 million light years away from us, if you imagine that there's an alien living in Andromeda galaxy and pointing a telescope at us, and that the way we would look to them is that we still look like that, because they see the way we were 2.3 million years ago. So that's what I meant, that when you look far away, you look back into the past. And this is the cluster of galaxies. And what you see here is that these yellow, the beautiful objects are individually their own galaxy, but about 100 of them are living together in a self-gravitational system. That's what is called a cluster of galaxies. And this particular one is about 2 billion light years away from us. So if there's an alien there and pointing a telescope at our planet Earth, the way we would look to them is like this. We are still single-celled organism. And that's the way we looked like 2 billion years ago. And this is one of the world record of the distant galaxy people have observed in telescope. And so if this is the image from Hubble Space Telescope, if you blow this region up, and if you further blow this region up, you see this little red smudge. And that is actually a full-blown galaxy, which is at the 13.3 billion light years away from us. So if there is an alien here and pointing a telescope at us, what they're going to see is actually nothing, because our solar system hadn't been born back then. So this is the idea that by looking far away, we can study what was going on at the earlier moments in the universe. So we would like to continue this path and see what was happening towards the beginning of the universe. But as I said already, there's some actually the block to that, because at some point we cannot use the electromagnetic waves anymore. So this image, for example, is actually in infrared, because what happens here is that faraway galaxies emit light, but as the light travels through the universe before reaching us, universe has expanded. And as a result, each photon had been also expanded accordingly, and their wavelength got stretched. So what used to be the blue light, for example, would eventually become red and infrared and eventually radio. So the reason why we see this red smudge here for a galaxy is an evidence that universe has gotten bigger since then. So that's the idea. So one way to actually understand this idea called redshift is that the faraway galaxies are moving away from us. So it's the same phenomenon as the listening to siren of the ambulance, that when the ambulance is approaching you, then the pitch of the siren appears to have a higher pitch. When it's moving away from you, then the pitch of the siren appears to have a lower pitch. And that's the Doppler effect, everybody here knows. And the same thing happens with the light or electromagnetic wave as well. So if you have a star that is supposed to be yellow, but if that is moving away from us, that is going to actually look red because of the Doppler shift. And of course, you know this. And in the case of the sound, there is the rest frame of the air that transmits the sound wave. So that you actually learn two different formulae, probably in high school, that depending on whether you are moving relative to the air or the other object is moving relative to you, you get different formulae. But of course, in the case of the light, there is no ether in the universe, so it doesn't depend on what rest frame, on the rest frame. So you have a universal formula like this one. But end result is the same if you expand this in terms of the speed of the object relative to this capital V, which is speed of light in our case. And then you have this linear relationship that the frequency is actually lower when the objects are moving away from you. So that's one way to understand this redshifting of the light coming from faraway object, because they are moving away from us. And that's the way you actually understand this Hubble diagram. So if you look at the object, which appears redder than what they should be by looking at, for example, absorption lines or emission lines, then you can measure the relative velocity based on how much the lines get shifted into the red direction. So that's how you measure the velocity of individual astronomical objects. Measuring distance turns out to be actually a lot harder than measuring the velocity. And that's because you can't just go out and come back and measure distance. So you have to use various different kind of techniques to measure distances. This is still a very controversial subject. So it turns out that how you measure distance accurately is still one of the major issues in astronomy, but at least you get some approximate measurements of that. So if you plot the velocity, how quickly the galaxies are moving away from us as a function of the distance to the galaxy, you find this linear relationship. So this is what is called the Hubble-Lemaitre law of the receding velocity. So velocity is roughly proportional to the distance. And the proportionality constant is what is called the Hubble constant, which is a big misnomer because it's not a constant. And as we talk about in a minute, in the cosmology, the expansion rate, which is this Hubble constant today, have been changing all the time. The universe was actually expanding a lot faster towards the beginning of the universe. So it's not a constant of time, but this is unfortunately called the Hubble constant. And it's given in this unit of about 60 kilometers per second per megaparsec. And megaparsec is the distance unit you use in astronomy. And kilometer per second, of course, is the velocity. So that's this constant h naught. So the fact that the velocity is linearly proportional to the distance is a sign that the universe is expanding homogeneously in as a whole. So that's the evidence that Hubble originally found that the universe is actually getting bigger. So the whole idea here is that it's not that individual galaxies are moving away from us. Each galaxy is more or less at rest, sitting on this grid. The idea, according to Einstein, is the space-time is of course not static. It can move and it's kind of alive. So the space-time can warp, twist, expand, collapse into a black hole, and also oscillate. That's the gravitational wave we have been hearing about this week. And so the idea is that this grid itself gets bigger. So if you are living in this galaxy and observing that galaxy over there, at one moment you have this distance, but at a later time you have a much bigger distance, and that is what you perceive as this galaxy moving away from you. So it's not that this galaxy is actually moving, it's more or less at rest on a grid point, but because the grid itself is getting bigger, you perceive that the other galaxy is moving away from us, and that's what you saw in this redshift of the light coming from the faraway galaxy. So another way of looking at the same phenomenon is that this galaxy emits a light, which is short wavelength, and let's say blue. But as the light propagates through the universe itself is getting bigger, as I just described a few seconds ago. So this light also gets stretched by the same amount. So as this blue light travels through space, depending on how much universe expanded since the light was emitted, the light gets stretched by the universal expansion of space. And so wavelength becomes longer, and that becomes the red light or infrared eventually. So even though the light was emitted in blue spectrum, when you receive it later, you receive it as the red light, and that's again the red shifting. So the Doppler shift I mentioned earlier is actually in some sense approximate concept because you are talking about this galaxy moving away from you. This is a more correct description of why light appears red and into the wave along the wavelength, and that's precisely because the universe itself is getting bigger. So that's the idea. So if the universe gets bigger, then and as the wavelength gets stretched, then you know the energy of the individual photon is given by this de Broglie's formula that for longer wavelength, the energy is low. So the photon actually loses its energy on its way, traveling through space. So each photon that's emitted in blue spectrum eventually arrives at the red spectrum when it reaches us. And so that photon has less energy than what it used to when it was emitted. So that is the idea that universe actually gets colder as it expands. So even though the universe was filled with photons initially, each photon gets the energy of each photon becomes lower as they travel through space. So eventually you have a gas of photons which have lower temperature as a result. So that's what is meant here. The universe gets colder because of the expansion. So if the universe is getting bigger and colder, when you sort of rewind the tape, going back to earlier moments, of course, the universe was smaller. I try to write it in smaller fonts here, and hotter in the past. So that's the idea of the Big Bang. So the universe must have started in small, very dense, and hot universe, and that's the idea of the Big Bang. But of course, we are scientists, so we just don't talk about it. We try to make sure that this really did happen. And so we look even farther away using telescope to see if there was really a Big Bang. And one of the things you discover is that if you point your telescope beyond the most distant galaxies, as I had talked about earlier, a few minutes ago, one point you see is actually nothing. So universe started out like a 13.8 billion years ago. But if you point your telescope to trying to study what you can see, let's say 13.6 billion light years away from us, you're looking at the moments. This is only like 200 millions after the Big Bang itself. And by that time, there were no stars. It took a while for the primordial gas to start to collapse into stars and form galaxies. So there were actually quite a period of time where there were still no stars around. And that is the era that is called dark ages in the history of the universe. So if you keep pointing at your telescope and trying to look farther and farther away, you start seeing these distant ever galaxies. But beyond some point, you're not supposed to see anything because there were no stars yet. The universe was completely dark back then. And then you try to see what was even beyond that. And that's when you see the picture of the Big Bang, namely the cosmic microwave background. So this particular picture comes from the European satellite called the Planck satellite. And by observing the 13.8 billion light years away from us, you can observe the way universe was 3.8 years ago. And that was a baby universe, as I mentioned on the second slide earlier today. And so you can observe the Big Bang. So you can really see that universe was hot. And this picture is actually extremely exaggerated. But what you actually see is almost completely uniform picture because the variation in temperature, which is depicted by little orange and blue, is actually tiny, only at the level of 10 to the minus 5. So if you don't exaggerate it, the picture you see is actually completely bland like this. So everywhere you look, you see early moments of the universe, but everywhere looks exactly the same. So that's the idea. But anyway, so by looking at this exaggerated picture, you see tiny variation of temperature depending on where you look. And that tiny variation of temperature turns out to be very important for the later discussions of inflation today. So anyway, so you do see the Big Bang, and so it's not just a talk, this is an evidence that indeed universe did start out small and hot. But at the same time, this is actually the limit how far you can observe using electromagnetic wave, because it's sort of the same idea like by looking at the sun. Of course, you are not supposed to look at the sun directly with your naked eyes. You have to protect yourself. But if you do, the only thing you can see is the surface of the sun, because the sun is the ball of hot gas, very dense. So light cannot penetrate through it, and it gets bounced around by Thomson scattering in the plasma of the interior of the sun. So only thing you can see is the surface of the sun. So in the same way, what you see in this picture, which is the picture of the Big Bang, is actually not the Big Bang itself, but the surface of the Big Bang, because beyond this point, the universe was hot, dense plasma, just like in the interior of the sun, but light cannot propagate through anymore. It gets bounced around, again, by Thomson scattering, by a bunch of electrons around it. So that's the limit you can observe with any spectrum of electromagnetic wave. So this is observed in a microwave, so the gigahertz, terahertz range of the radio, because the light emitted back then in the optical spectrum got redshifted to the radio wavelength by the time it reaches us, the same ideas as we talked about with the galaxies. And so that is really due to the expansion of the universe since then. So the universe expanded about 1,300 times from this moment. And that's why the optical spectrum ends up being radio spectrum. But nonetheless, this is how far you can observe by any electromagnetic spectrum. Beyond this, you can never, ever see it with any electromagnetic wave. So that's what I meant by the wall. So this is the wall you can see with any electromagnetic wave. And so this cosmic microwave background had been discovered by Penzias and Wilson using this antenna, which was initially developed for communication purposes, but they actually pointed to the sky and they actually observed some strange noise. And I actually had a pleasure of visiting this antenna together with Robert Wilson himself. And he's a charming guy. And so he actually did the following trick. So at the focal point of this antenna, he took out his iPhone and he played the sound of CMB. And of course, what they observed is the radio signal, but he actually transcribed the radio signal into the sound, and he played it at the focal point, which actually broadcast the sound to the surrounding area because the antenna can work the other way around. And I can play the sound to you. So it's basically the noise. So it's not a pleasant sound like a chirp you might have heard from the collapse of black holes. It just sounds just a white noise, but this is the noise they heard. And they were puzzled by this noise because the same noise came from every direction they pointed the antenna to. This is in New Jersey. The one thing they thought about first was, okay, we are close to New York. Maybe the radio is coming from New York City, but pointing the telescope away from New York City, they still heard the same noise. And they excluded all the other potential candidates of the noise they can think of. And eventually they decided that, okay, this is coming from the universe itself because it comes from all directions. And that is the signal of the cosmic microwave background at the end of the day. So this is how we actually managed to see or hear the Big Bang. And these days, we use these satellites to observe the cosmic microwave background. And what you see here is the spectrum of the cosmic microwave background, the intensity versus wavelength. And it says theory and observation agree. And you might be skeptical about the statement because you don't see any data points in the error bars. It turns out the error bars are drawn on this plot, but error bars are so tiny that they are completely masked by the thickness of the theory line. This is actually the best black body radiation you can observe in any experiment, probably. So this is really the telltale sign that the cosmic microwave background had been emitted by something that has a thermal spectrum, has a temperature, and universe was indeed hot. But of course, the temperature of the photon had been redshifted since then. So what we observe today is a temperature at the level of 2.75 Kelvin or so. So it looks very cold now, but if you just go back 1,300 times higher temperature, of course, universe was indeed hot. So that's how we know that the universe it really did start with a Big Bang. And observation of the CMB background, John Mather was the primary responsible for measuring this thermal spectrum to verify the black body radiation law. George Smoot, one of my colleagues, was primarily responsible for taking the picture, which shows this tiny temperature variation. And then they co-received the Nobel Prize because of this achievement. And this is the picture they took at this stage. It looks much more low resolution than the picture from Planck satellite. This is the Kavli satellite they actually launched back in 1990s. But this is the first time that we ever detected these tiny temperature variations depending on which direction you look. And this was actually incredibly important thing because this tiny temperature variation shows that the density varied from one point to another. And slightly denser part of the universe eventually became a lot denser, and I'm going to talk about this later today, and that eventually collapsed into the stars and galaxies and us. So these tiny variation temperature is basically where we came from. So this is the incredible achievement this Kavli satellite did, and that's the reason for the Nobel Prize. So that's the picture of the Big Bang. And George is also a very charming person. And so one of the things the Nobel laureates, of course, have a advantage of is that on Berkeley campus, there are so few parking lots and there are places reserved only for Nobel laureates. And the day that he actually got the phone call from Stockholm, he decided to drive, even though he normally walks to the campus, he decided to drive and park his car on one of these Nobel laureates parking lots. And he got a ticket. And the reason being that, the only thing he got by that point was the phone call. He hadn't received the prize yet, so he was not allowed to park on this Nobel laureate parking lots. So he actually paid the fee, it turned out. So poor guy. But anyway, so this was really worth Nobel Prize for sure. And the picture of the Big Bang got a much better over time. So the next satellite that did the same observation is WMAP. That's a satellite from NASA. And now Planck. And the people used to joke about the fact that the universe seemed to know Stephen Hawking. You see the initial SH on this picture. So the sort of a well-known the talk in the community. But when the Planck satellite came out, this is a European satellite from ESA, the initial SH sort of disappeared in the noise. So the universe didn't know Stephen Hawking in the end. So here's the idea. So when you look far away, you're looking at the earlier moments of the universe. And before this point, you observe the cosmic microwave background, the universe was in a state of plasma. So there were no neutral atoms because the universe is so hot, the neutral atoms dissociate into the gas of electrons and protons and nuclei. So this was a state of the plasma, as I said. And because you have these free electrons, then the photon would interact with the free electrons by Thomson scattering, which is a very big cross-section in this dense universe. So the photons could not travel freely. It gets bounced around all the time, just like the interior of the sun. But only from this point, when all the electrons get bound to the nuclei and to form neutral atoms, then the photons start to propagate freely. And that's the photon that reaches us today. So that's the idea of cosmic microwave background. So that's the wall I mentioned at the beginning of my talk. So using electromagnetic wave, this is the best you can do to observe the earliest moments of the universe. It's definitely early, but we are interested in what happened even earlier from this moment. And that's where gravitational waves will come in, we believe, as a new tool to study the early universe. Okay, so that's the idea. So we have to now come up with a theoretical description of how universe expands. So I'd like to do it in a very sort of a cheesy way using a Newtonian mechanics right now, and eventually connect that general relativity. So idea of the Big Bang is sort of exactly the same thing as standing on the ground and throw the ball you have in your hand upwards with the initial thrust. And initial thrust is basically the Big Bang. And as the ball keeps going up, the gravity pulls it down, so it should slow down. So that was the idea of the expansion of the universe. So to put it in a mathematical formulation, just imagine that you have a collection of some particles or massive objects. And so that just imagine they are expanding in a spherical fashion. And if we have a test mass on the edge of the sphere, then the force it feels, of course, is the gravitational force coming from this entire mass within its radius r. So that's the usual Newtonian mechanics. And because F equal ma cancels a from both sides, and that's the equivalence principle, you can get this acceleration, which is different by the second derivative of this radius of the sphere. So putting these things together, you find this equation, how this radius would change as a function of time in terms of the gravitational pull coming from the total mass in this system. So it turns out that the way the universe expands is exactly the same equation. So the equation we use is basically the same thing as the Newtonian mechanics. So that it would immediately tell you that there are three possible solutions to it. So if the initial thrust is not big enough, then the ball you have thrown upwards cannot escape the gravity. So it would eventually stop and come back down. So that's one solution to this equation. If the initial thrust is big enough to escape the gravitational pull beyond basically the escape velocity, then the ball would escape the gravity from the planet and then just keep going with the constant speed eventually. So that would be another solution. And if exactly in the middle between the two, then you have the energy, which is exactly the same amount to escape the gravitational pull. So in this case, you find a solution that grows like the square root of time. So these are three potential solutions you find also for the expansion of the universe as well. And so just knowing the Newtonian mechanics, this gravitational pull tells you that there's something conserved, namely the energy. So this is the kinetic energy per mass, and this is the potential energy per mass. And this total energy per mass is supposed to be a constant in this motion. And correspondingly, you also have the same constant in the case of expanding universe too. So this escaping solution would correspond to positive energy. This collapsing solution, where universe expands, stops, come back down and collapses back to a point, is the case of the negative energy. And this solution in the middle is the exactly zero energy solution. So you can draw the potential energy for this. So if you have this potential energy given by this gravitational potential, depending on what is the total energy, if you have the energy less than 0, then it just keeps going, but eventually hit the potential wall. That's where it stops and come back down. That's this solution at the bottom here in green. Then the red solution has a positive energy. So that is the case when you escape the gravity and keeps going. And the blue one is exactly in the middle with a 0 energy. So that's exactly what happens with the expansion of the universe as well. So by writing this equation being a constant, you can write an equation on how universe gets bigger as a function of time. So that's this equation here. So just rewriting the constant of energy in this particular fashion. So this is R dot. I divide it by R, and R dot over R is what is called expansion rate. And the Hubble constant you saw on some of the earlier slides refers to this ratio R dot over R, because R dot is the velocity over the distance R was the Hubble constant. That's the Hubble Lemaitre law. So R dot over R is the Hubble constant now, but of course it was different number at the earlier moments of the universe. And this expansion rate squared then is written by this gravitational potential over R squared now. So this is M over R cubed. And another term is this constant epsilon over R squared. And in general relativity, we write it in a slightly fancier form. So instead of calling this epsilon, we call the K with a negative sign. And this K happens to be actually related to geometry of the universe that comes up on the next slides. And we also rewrite M over R cubed as a mass density or energy density. So the R cubed times 4 pi over 3 is the volume of the sphere. So by rewriting it in terms of mass of the volume, you'll find this additional factor of 8 pi over 3 at the end of the day. So 4 pi over 3 times 2. And so this is the form we normally see as an equation called the Friedmann equation. So the way universe expands is obtained by this equation. And even though I use this non-relativistic Newtonian argument to derive this equation actually turns out to be true even in relativistic theory, where the energy density rho may consist of relativistic particle species instead of non-relativistic gas. So it turns out this equation is still true in a relativistic regime, and that's the Friedmann equation we're actually going to use over and over again. So the way you actually get the same thing from general relativity is to write, of course, the metric. I'm sure you have seen this many times in the previous lectures for general relativity. And the metric has the universal time. But we also have this what is called a scale factor, which describe basically the size of the universe. And depending on the geometry, whether the universe is completely flat like a flat surface here, or just like the surface of a sphere, which has a positive curvature, or basically like a mountain pass, where you have the negative curvature, you have this constant K. So this constant K depends on what kind of geometry you are in. And the reason why there are only 3 choices here is because to the extent we observe the universe appears to be totally homogeneous and isotropic. So every place looks the same, homogeneous, and every direction looks the same, isotropic. And if you ask the mathematician, what is a possible space which is homogeneous and isotropic in 3 dimensions? And they will tell you that there are only 3 possibilities, and hence these 3 choices here. And these 3 choices are determined whether K is 0 or positive or negative, and hence 3 choices for the metric you can write. So this thing in the parentheses tell you which geometry you have for the universe. And this geometry expands as a whole that is given by this scale constant R of t, and this is the metric for the space-time. So if you use this space-time metrics and put that into Einstein's equation, the Friedmann equation you saw on the previous slide would pop up. And hence, this is really a consequence of general relativity, even though I use this cheesy derivation based on the Newtonian mechanics. And because now that we have this metric, and for different 3 geometries, you can actually start testing what the curvature of space actually is. So the idea is simply by drawing a triangle, and inner angles would add up to 180 degrees if the triangle is drawn on a flat surface. But as you know, on a surface of a sphere, like on a surface of a planet, the straight lines are great circles. And then the triangle have the inner angles adding up to something bigger than 180 degrees in a positively curved space. If you go to this mountain pass, which is negatively curved, the inner angles would add up to something less than 180 degrees. So if you can draw a big circle, a big triangle in the universe and measure the sum of inner angles, then you can tell what geometry you have in our universe today. And it turns out that it's consistent with flat, with the level of the 1% accuracy. And I will show you the evidence of that in a moment. So we seem to be living in a flat universe where you can take this k to be 0. And then this R of t describes universal expansion of space. And that's how we describe the expanded universe using the Friedmann equation. And as I mentioned already, this energy density can vary depending on what's inside the universe. Our universe now seems to be non-relativistic. And if you insert non-relativistic energy density, then it's given by mc squared, energy per particle, times the number density. Then the number density, of course, goes down like 1 over volume. So the energy density then goes down like 1 over volume. So it goes down like r to minus third power. So if you stick in out the minus third dependence here and solve this differential equation, ignoring this curvature term, you'll find that the radius of the universe grows as a function of time with a 2/3 power, just by solving this differential equation. When the energy density is relativistic, that was the case in the early universe, then energy density basically goes with temperature to the 4th power. And that the reason for this is that, let's say you imagine a gas of photons, and the number of photons is conserved as the universe expands. So it goes down like 1 over volume, just like in the case of non-resistance case. And the temperature goes down like 1 over r as well, because each photon gets stretched by the expansion, as I talked about. Energy of photon goes like 1 over r. And temperature, of course, goes with energy of the photon. So temperature goes like 1 over r. So T cube out of this 4th power is how the number density of photon goes down. But the 4th power comes from the fact that each photon has lower energy as the universe expands, hence the 4th power. So the rho goes down like 1 r to the minus 4th. If you put that in here, then you find that the size of the universe goes like the time to the half power. But there's another interesting solution we will think about later. It's the case when energy density of the universe is constant. So that sounds like a crazy thing to do, because as the universe expands, everything in the universe gets stretched and become dilute, and energy density we expect to go down. But just for the sake of argument, let's think about energy density being constant for now. Then the right-hand side of the equation is constant, again, ignoring the curvature term. Then r dot over r is constant, which means r dot is proportional to r, which is this exponential behavior as a function of time. So r dot just pulls out this h from the exponent, which is proportional to still r, and that will be the solution when you have this constant energy density. And constant energy density is often called vacuum energy, because empty space seems to have a energy per volume, which sounds like a crazy idea, but we'll come back and talk about later. And then you have this exponential expansion. So the main message here is that depending on what kind of thing is in the universe, whether non-relativistic gas, relativistic gas, or vacuum energy, universe expands differently, because what Einstein equation tells you is that the metric and the curvature of space is determined by the energy momentum tensor in the universe. And when you solve this equation, that's this Friedmann equation, you find the expansion law of the universe. So anyway, so this is the way we now understand why universe is expanding depending on what's inside. So that's the Friedmann equation. And then let me talk about some idea how we can understand what's inside the universe today. So I already mentioned this hot, dense plasma that was going on in the early universe that emitted the cosmic microwave background. And the cosmic microwave background hence knows basically what was going on in this moment. And what was going on in this moment is that you have this fluid made of plasma. And whenever you have a fluid, you can have sound wave in it. And the sound wave is great because if you actually strike different objects, if you strike a wooden desk, or if you strike a metallic pipe, you get different kind of sound out of it because the basic resonant frequencies and the overtone structure of the sound knows about the medium you're striking. So in the same way, if you strike this primordial plasma before the time of the CMB photon was emitted, there's a sound wave, and the spectrum of the frequency of the sound wave knows about the medium that actually in which the sound wave propagates. So analyzing this cosmic micro background, you can learn a hell of a lot about what was going on and what existed at the point of this the recombination when the primordial plasma became the neutral atoms. So the idea is to take this picture of the Big Bang I showed you earlier, and this is of course the picture of the 4 pi, the solid angle, which is drawn into this ellipsoid just because I can't draw the 4 pi solid angle in 3 dimensions on a 2-dimensional screen. So this is meant to be actually a 2-dimensional sphere. And you actually have a plot of temperature as a function of the angle, of the polar angle and azimuthal angle at every point on this picture. So when you have a sphere, then what we learn in quantum mechanics class is that you can expand any function on the sphere in terms of the spherical harmonics. So what you do is to expand this temperature as a function of theta and phi in terms of a linear combination of spherical harmonics determined by L and M. And that tells you what is called the power spectrum, namely that you take this coefficient ALM and take the absolute square and sum over M. So you still have L left, and that gives you a number for every L in this multiple expansion of the sphere, and you plot it, and that's this picture over here. So as a function of L, you see these wiggles, and these wiggles are meant to be the spectrum of the sound that was propagating in this primordial plasma. And so by analyzing the spectrum of the sound, you learn what was there in the primordial gas that transmitted the sound back then. And so if you vary various parameters, you can find this spectrum actually changes. So one important information is this angular resolution, which is L. And when L is low, then you are looking at this 2-dimensional sphere with a very low angular resolution. But when you increase L, you're looking at a finite structure. So that's the picture that was actually, in this animation. Sorry, it's not running. Oh, something's wrong with this animation. Something's wrong. I apologize. It's not running. But the idea is that when you actually go from this very low L band to high L band, you're looking at much finer structure in the temperature map you saw on the previous slide. And one of the things you can do then is to looking at this map. And then I mentioned this idea of drawing a big triangle in space. And so the idea is that this peak corresponds to basically what is called the sound horizon in the early plasma, where the sound propagated basically over the entire causally connected region. And so you actually know the physical size of this the peak in the frequency of the sound wave. And so this is determines your triangle, right? So if you know the side, one of the side, which corresponds to some physical scale, which is the sound horizon in the early plasma, and you know the distance, because this is a 13.8 billion light years, so you know the distance, you have determined all the 3 sides of the triangle. Then you measure this inner angle. And because you have already determined the triangle already from 3 sides, the inner angle can tell you whether you are on a flat surface or in this positively curved space where angles should look bigger, or negative curved space where angles should look smaller than the case of the flat triangle. And so as you change this curvature space, this peak changes. And again, I'm sorry, the animation is not working, I apologize. So what it's meant to show is that this peak would shift left and right, depending on what curvature you have in space. So by looking at the peak of this the sound wave spectrum, you can determine the curvature of space, and that's what I meant when I said that it's consistent with a flat universe with a 1%. You can also vary the matter content of the universe, which is dominated by dark matter. We still don't know what it is. It's not atomic matter, something totally different, and that's a fascinating subject of its own. But again, once you actually change the content of the matter, which provides the gravitational potential, that the amount of dark matter you have basically gives you the depth of the potential. And if the potential is deeper, then the sound wave gets amplified. So basically the height of this peak will tell you the amount of matter. And again, I'm not sure, oh, it's working now. So you can see the height changes as you vary the amount of matter. And when you also change the number of atomic component of this primordial soup, then atoms, namely electrons, would interact with the photon. So the electrons are not just the gravitational potential, but really coupled to the wave that propagates inside this medium. And so the wave, of course, has peaks and troughs. So depending on how much atoms you have, you can change odd, even peaks on a relative height. And this one is not working. I don't know why something is working, something's not working. I apologize again. But we actually change the relative height between even and odd peaks. And that's how you can determine the amount of atoms or electrons you had in the primordial spectrum. So that's how we came up with this pie chart, which I'm sure you have seen before. So the stars and galaxies are a very small amount of the energy density in the universe. There are some component that is given in neutrinos now that we know it has a mass, but the rest of the energy density is really dominated by three components, namely ordinary atoms, that's about 5%, and the dark matter, that's about 27%, and something called dark energy, which is 63%. So the reason we know this pie chart is because we could analyze the spectrum of this the sound wave from this temperature map of the cosmic microwave background radiation. And so, so we know the content of the universe. And so that's something we learned greatly in the cosmology today. And it has been remarkable progress of this field since I entered into science back in grad school. Then these data start to come out. So I actually graduated my PhD in 91. 93 is when this Kavli result came out. And now we have this Planck result. So we have learned great deal with a great precision now about the universe today. And so this has been a huge, amazing, exciting decades of the progress. And one thing that remains as a mystery today is that we don't seem to have any antimatter in the universe, 0%. And I will come back and talk about this probably tomorrow. So that brings us to the discussion of inflation. And let me just check how I'm doing with my time today. So it's been about an hour since I started. So maybe this is a good place to stop and start before we actually start talking about inflation to see if there are any questions.
I have a question.
Go ahead.
So actually, I have many questions. So when you were explaining the fact that the photon gets stretched an extra dimension or an extra factor because of the wavelength, nothing like that happens to particles like electrons with their de Broglie wavelength.
No, it does. It does happen the same way. So every momentum gets redshifted. And in the case of electron, if you think of non-relativistic electron, its energy is dominated by mc squared. Kinetic energy is typically smaller than that. So you don't see appreciable change in the energy because it's just given by mc squared. But the momentum, which is given by the de Broglie wavelength, would redshift the same way as the photon does. So that's a universal effect. Every de Broglie wavelength gets stretched by the expansion of the universe. And then for the electron, as I said, because it's non-relativistic today, you don't see that impact of it. But when you study, for example, the neutrinos, they used to be relativistic at the time of this cosmic microwave background temperature. So the energy was dominated by the kinetic energy from the momentum. But now that the momentum got redshifted to the extent that became actually comparable to its rest mass. So in the case of the neutrino, you really have to study this impact of how momentum redshifts as the universe expanded.
I see, awesome, thank you. And the other question was, when you were talking about the fact that if you have a flat geometry, that implies an expansion rate of t to the 1/2.
Mhm.
After that, you also started commenting that depending on how much density of top or what stuff you have to make your
Mhm.
density, that could change as well the expansion. So I'm just a little bit confused. If I just tell you I have a flat universe, that means no matter what, we will expand at a rate of 1/2, or changing the content will also matter.
Yeah. So the what I meant by flat is that k can be taken to be 0 as for a good approximation, right? So I can ignore the second term. But this energy density rho would depend differently as the universe expands, depending on whether you have this non-relativistic gas, and we call this matter generically. So when we say matter dominant universe, we say the content of the universe is dominated by non-relativistic objects. So in this case, rho would go down like 1 over volume. And when you solve this equation, you find actually times the 2/3 power, not 1/2. But when you have instead relativistic gas, and generically we call this radiation and talk about radiation dominated universe, then the rho goes down like r to the -4th, because each photon also gets redshifted in its energy. And then you solve this equation and find this goes like time to the 1/2 power. So depending on how energy density gets diluted as the universe expands, you find different solution. So that's what I meant, that the expansion universe depends on what's in there.
But when you have, if you go to the previous slide, when you have in that beautiful drawing, you see that you have the curve to the t1/2 associated with the flat universe. And previous to that, you were not talking about any content or type of content.
Thank you. So that's a very good question, because I glossed it over. So I actually made the assumption here that the energy content of the universe is actually given by the matter and the curvature. So that's the combination I assumed when I made this correspondence between this geometry and different solutions to the Friedmann equation. So I had made an assumption, which I failed to mention, and that's why you're actually pointing out. So thank you for actually asking that question.
No, perfect. Thank you so much. Okay, I will let other people ask.
Can you actually show that slide 33? I want to understand because you didn't have animation, so.
Sorry about that.
No. So about the measurement of the geometry. So the position of the CL. Do you have a slide?
So this slide?
Yes. Right. So you said that in the flat, for example, in the triangle case, two lengths is basically corresponding to the age of the universe, right? And then the opening, the length is corresponding to the position of the first peak. Is it correct?
So what I'm saying is that this peak, it corresponds to the physical length, which corresponds to the wavelength of the sound in the early universe. So you know the physical length here. And we know the distance to the CMB surface, that's the 13.8 billion light years. And so you have determined 3 size. So the only thing you measure then is this inner angle, and that corresponds to this L. So L of about 100 corresponds to about a degree. So the 200 corresponds to about a degree. So you are measuring this, the angular opening of this where the peak is, which corresponds to sort of a typical size of the fluctuation in density. You can sort of see it, right? It's about this size. So this kind of size is roughly how big each blob of high temperature and low temperature is. So that's the angular scale you're measuring, which you can do with the naked eyes from this picture. So now you know the angular scale, and in spherical harmonics, L is basically inverse the angle. So you know what that what corresponds to in terms of L. So you measure the location of the peak in L, and that is the measurement of this angular, the inner angle of the triangle. And that's how you actually measure the curvature.
Thank you.
Can I ask a question from the same
slide?
Can you comment on why the height of the second and the third peak are same, or at least very similar?
Oh, this is for a specific parameter. And if you look at the real data, then indeed they are similar. But that's determined because of the various contents in it. For example, I mentioned that in the case of the contribution of atomic matter, then this height between the relative height between even and odd peaks change.
Yes.
And that's actually shown in this the three-dimensional plot here. So these two peaks being similar is in some sense an accident of the composition of the dark matter and the atoms, because the dark matter is basically overall the size of the amplitude, and the atoms is a relative amplitude between even and odd, and that's conspired together to give you something more or less the same height for the second and third peak.
Mhm. Okay.
Are you sharing your screen? I cannot see your screen.
Oh, sorry. Not to make a mistake of leaving. Okay, yeah, sorry. So maybe I'm not showing it. So if you look at the data in the second and third peak look very similar in height, but that's because of the conspiracy in some sense that the dark matter content basically tells you the overall size of the peaks, while the component of the atoms give you the relative height between the odd and even peaks. And so they somehow conspire together to give you more or less the same height for the second and third peak. That's what I wanted to say. Sorry, I wasn't sharing the screen.
Hey, Toshi, I have a crazy question.
That's scary.
De Broglie wavelength,
Yes.
ultralight dark matter, 10 to the minus 22 eV is about a kiloparsec, right?
Mm-hmm.
And if you run it backwards and you assume that the de Broglie wavelength was 1,300 times, I guess, shorter, right? Back at the C and B time.
Right.
Would that, or would it not have consequences for structure formation to the extent that dark matter interacts or anything else? In other words, it's not a set, because of that long de Broglie wavelength, that you would think that it could have consequences, but would it?
Well, it would, but the people make the following assumption though. So in the case of very, very light scalar field dark matter, like what you're talking about, a 10 to the minus 22 electron volt, people assume that even though it's so light, it was already non-relativistic in the form of basically Bose-Einstein condensate already at the time of the cosmic microwave background. So the de Broglie wavelength was basically the momentum was basically nearly zero, and the de Broglie wavelengths are really very long, so that it stretching further, it was not going to actually change things very much. That's the assumption people make.
Right.
How exactly you achieve that initial condition is an issue of writing down the theory for it. But once you do make that assumption, it had been non-relativistic all along. And so that's how that kind of light dark matter can still do a structure formation properly.
Thank you.
Any further questions?
I think you can go ahead.
Okay, so let me go back to the slides, and then finally we start talking about inflation. Okay, so this is actually a movie based on the real data. The Lonsdale Sky Survey is a project that actually measured millions of galaxies, and they actually put each galaxy from the data at the right location and right shape into the computer. Then you can pretend that you are doing this incredible flyby in a 3D fashion in your computer. Of course, if you really want to do this kind of flyby, you have to travel at a speed about 100 trillion times faster than the speed of light. So don't try this at home. So you can't really do this, but at least this gives us a very valuable piece of information, namely that no matter how far you go, universe looks pretty much the same. And that's the idea of the homogeneity of the universe. Namely, universe is the same everywhere you go. So by and large, the universe is homogeneous and isotropic. And that's what I mentioned when we talk about these three different geometry of the universe today. So Lonsdale Sky Survey created this two-dimensional map as well, where each dot corresponds to a galaxy. So you have something like 1 million galaxies in this map. And the black portion is not that the galaxies don't exist there, that they have not been observed yet. Because you have a finite amount of time and a finite amount of exposure, so you can't observe the entire universe, even though they did observe millions of galaxies. So this part is just not being observed yet. So the part they did observe, they put a dot for each galaxy they did observe, and so that's the map, which is something like 2 billion light years across. And again, by and large, universe is homogeneous and isotropic. This is where we are. Depending on which direction you look, you are supposed to see more or less the same kind of universe. But you, of course, do see there are some clumpiness as well. And these, the linearly stretched clumpiness is called filament. The parts that look kind of empty is called void. And you have this kind of large-scale structure of the universe today. So the way we understand is that this is basically an impact of the initial variation in temperature we talked about at the level of 10 to the minus 5, but which have been nurtured and grown into a nonlinear structure we see today simply because of the gravitational pull. So we will be actually talking about that. So more or less uniform with small wrinkles, and that's the way universe looks like. I already mentioned the fact that the temperature is basically the same no matter which direction you look. And this is the same plot of the comparison between black body radiation and the data points I showed earlier. But in this plot, the error bars are magnified by 400 times. Otherwise, you don't see the error bars. That's what I meant earlier, that the error was so small that it was buried in the thickness of the line. If you magnify by 400 times, you see error bars. But again, you see this incredible agreement with the black body radiation, and that's how we got convinced that universe had a temperature. But the point here is that every direction looks the same. And this is actually a very strange fact, right? So this is, I think, what Andre Linde told me about a sort of analogy. So suppose you're a world explorer. You have discovered 2 remote islands in very different parts of the planet. But when you go to these islands, you find that they speak the same language. And you don't need to be anthropologist to come up with a theory that, these people came from the same place. That's why they share the same language. And that's not even the same language, right? Because we're talking about the accuracy at the level 10 to the minus 5, they are even same dialects. Surely they must have come to the same point. They must have been communicating before. So it's the same idea here. So if you look at this map, this is actually very strange because the photon coming from one end of the universe just reached us now. That photon did not have time to travel to the other end of the universe and communicate with the other parts of the universe. They must not been able to talk to each other. But how come that they have exactly the same temperature? How did they manage to arrange themselves to have the same temperature? So that seems to go beyond causality. Something is wrong with this. And this is the problem called the horizon problem. Somehow, the entire universe seems to have arranged themselves in a way that every part have the same density, every direction looks the same. How did they arrange that? So the idea going based on this analogy to remote islands is that, okay, entire universe we see today must have been together at some point. They must have communicated with each other, so they arranged themselves to have the same temperature everywhere. And that small universe where everybody could talk to each other was a microscopic universe, somehow turned into macroscopic universe today by an incredible stretch. That's why one end of the universe and the other end of the universe seem to be so far away from each other, they didn't look like they have talked to each other, but they actually secretly did because they were together in this tiny, tiny universe at the beginning. So that's the idea of inflation. So universe started out with a microscopic size. We are actually talking about the entire universe we see today being microscopic at the level of 10 to the minus 26 centimeters. Much, much smaller than even the nucleus. It's a really microscopic universe. But somehow, that tiny, tiny microscopic universe where everybody could talk to each other and arrange themselves to have the same temperature got stretched by an incredible rate to a macroscopic universe we see today. And that's the idea of inflation. So this is really mind-boggling. So we used this word inflation casually as if it was like an economic inflation of 4% a year. No, it's not nowhere close to that. It's an incredible expansion that happened at the beginning that stretched this tiny, tiny microscopic universe to a macroscopic size we see today. So that's the idea. But how is that possible? So I mentioned this idea already. When universe starts with a Big Bang, everything sort of spreads out. And the what spreads out, of course, pull each other by gravitational pull. So the only thing it can do is slow down. It's hard to imagine this huge expansion in an accelerated fashion can happen. But that's when we come back to this slide. When you have universe, which is dominated by this constant energy density, which I call vacuum energy, then the universe would expand exponentially. And that's exactly the kind of thing we need. And this is also an accelerated expansion. If you take the first derivative, that pulls out this expansion rate h out from the exponent. If you do the second derivative, that's the acceleration, you again pull out h from the exponent, which is positive, namely that acceleration is positive, the expansion accelerates rather than decelerates. So naive picture I mentioned on previous slide that gravity only pulls and slows expansion down is actually not true when you have this constant vacuum energy. And constant vacuum energy is a very strange thing. And when you actually make the universe bigger from, say, the one volume to twice as big space, then volume becomes 8 times bigger. Then in the same volume, energy becomes 8 times bigger by definition, because I assume the constant energy density. So energy keeps multiplying by an expanding universe if you assume this constant energy density. And if you use the first law of thermodynamics, change of energy is minus PdV. So normally, pressure is positive. So when the volume expands, energy goes down. But here you see the energy is going up as the volume going up. So you're talking about something with negative pressure. So mathematically, everything is consistent. First law of thermodynamics tells you when the pressure is negative, energy can go up for the growing volume. And indeed, when you have the constant vacuum energy, energy momentum tensor is proportional to the metric. Therefore, the pressure is negative because the spatial component of the metric has opposite sign from the time component of the metric. So energy density grows because of the negative pressure. So mathematically, there's nothing wrong. It's just that it looks very strange, bizarre to us. But if you make that assumption, you find this accelerating expansion, which achieves this inflation idea I mentioned on the previous slide, so that we can understand why every direction looks the same. So that's the idea of inflation. So let me just do just once again. If you have this Friedmann equation and assume this constant mass density, then R dot over R, that's the Hubble constant, which is not a constant I mentioned earlier, is a constant. So in this case, in constant energy density, Hubble constant really is constant. And if this is constant, you have R dot over R being constant. Therefore, dr dt is constant times R. And again, I get this exponential solution. So I'm repeating myself here, but I'm just reinforcing this idea that constant energy density gives you a constant Hubble constant. Very strange way of saying it, but that's the name for the Hubble constant. And with the constant Hubble constant h, I get this exponential expansion. And that would achieve this incredible expansion we need to explain this horizon problem, namely, how come the different parts of the universe look the same, even though they don't seem to have communicated with each other? So we need to actually go back to the earliest moment when universe was microscopic. Everybody could talk to each other, arrange themselves to have the same density and temperature. And then you use this exponential expansion to stretch them away from each other by an incredible distance. And only now they are coming into our sight. And that's the idea of inflation. And so we talked about different energy content of the universe. Here, you're talking about this constant energy per volume. So if the universe becomes twice as big, volume becomes 8 times bigger. So this energy becomes 8 times bigger. So total energy keeps growing like volume because the size of the universe goes like e to the ht. That's a solution we had on a previous slide. Volume goes up like e to the 3ht, and that's how energy grows. So energy grows like volume. And so because energy becomes bigger, the Friedmann equation makes the expansion faster. And when the expansion becomes faster, the size becomes even bigger. And then energy grows even more because it goes with the volume, just keeps getting faster and faster. And that's the meaning of this exponential solution. So the technical term we use for this, that the volume just keeps growing and energy keeps growing as well, that makes the expansion even faster as a result, is called the ultimate free lunch. Somehow energy is just keeping wearing out from the empty space and makes the universe expanding faster and faster. So something looks wrong, right? We know there's no such a thing as a free lunch, as this cartoon says. So we have to somehow understand what could be responsible for this exponential expansion. And here's this idea. You take a particle and put that on a hill on a potential energy. And of course, in practice, we're talking about a scalar field, some particle which is described by the wave equation with no spin. And so this particle is sitting on this slope, but just imagine that there is some kind of fluid over here that gives a friction that makes the motion of this particle rather difficult. So it wants to come down this hill because the gravity pulls it down, but the friction slows it down, so it comes down very slowly from this slope. And while it's coming down very slowly on this slope, you have this potential energy nearly constant for a while. And this potential energy is the constant energy density I talked about in this ultimate free lunch. So as this particle slowly comes down this hill, you have a period where the potential energy is more or less constant. That gives you constant energy density. And as a result, the universe expands exponentially. So let me show the animation. Hopefully this one works, that this comes down very slowly, and then universe expands exponentially, and this size of the universe is drawn on a log scale. So linear slope would be exponential expansion. So here we go. So here's exponential expansion. But once it comes to the bottom of this potential, it goes swish, swash, oscillates around the minimum like a harmonic oscillator. And that's the case when this exponential expansion no longer happens, because the particle going back and forth like a harmonic oscillator is what corresponds to the matter, or known with this particle I mentioned in this energy density of the universe earlier. So that gives you only power law expansion on this log scale that looks completely flat. So the idea of inflation is that if you have this kind of scalar field coming down the potential very slowly, it generates this exponential potential approximately, but not exactly exponential, because energy density is coming down as a function of time. But for a while, it looks very good exponential. But eventually that will slow down and turns into power law expansion. And that's the idea. So this ultimate free lunch I mentioned is not completely free. You need to have this kind of scalar field that slowly comes down to this potential, which leads to more or less constant energy density for a while, that leads to more or less exponential expansion. And that's the idea how we describe this inflation. So what we do in practice is write down the field equation for a scalar field in an expanding metric, G mu nu. And by putting in this, the Friedmann metric I mentioned earlier in the expanding universe, that depends on this scale parameter. You can just write out this metric part of the scalar field equation that turns into this. So this double dot is what you have for normal mechanics, namely that acceleration is given by the force, which is the gradient of the potential. But because this metric depends on a scale factor, r of t, this derivative can have time derivative hitting that time dependence of r. That gives you r dot, which is basically the expansion rate. You find a piece in here where this time derivative hits r, giving you h. The other time derivative acts on the field. So you find this 3h phi dot term in the field equation. And this equation basically tells you that force comes with the velocity, which is nothing but the friction. So this term is called the Hubble friction, that's a technical term, which slows down the motion of the scalar field in the expanding universe. So during inflation, universe is expanding like crazy. You have a big expansion rate that's nearly constant given by the potential energy, which is nearly constant. So in this nearly constant Hubble constant, that acts as a friction term so that the acceleration is negligible for the scalar field. That's why, as you saw in the previous animation, it seems to come down the hill nearly with a constant speed. That's the terminal velocity in a medium with a friction, like the raindrops are reaching the terminal velocity before it rains on us. So that's a situation where you balance this friction term against the force. So you ignore this double derivative completely. Then you can solve this equation, which is a simple first order differential equation for phi. So as an example, let's take the parabolic potential. That's the example I used on a previous animation. So you know the potential, which is parabolic. And then you solve this equation. And you also need to actually look at this expansion rate as well, because the Hubble is actually square root, basically, of this potential energy. So by using the Friedmann equation, you know the Hubble constant is square root of potential, which goes like phi. You put that in here. Then phi dot goes like phi. Then you can cancel phi. You find phi dot is constant. That's why you saw in the animation, really velocity looked like a constant. And that's the solution here. So with a constant speed. Then you stick into this Friedmann equation again. Then you find the solution to r, which is almost exponential, even though exponential expansion slows down by t squared piece. So that's what you saw. So it was almost exponential expansion, but exponential expansion would be less exponential as time goes on, and eventually turned over to the power law solution. So let me show this again. So here, ball comes down, with a constant speed, nearly, and exponential expansion, but exponent slows down. And when it starts to oscillate around the origin, then you can no longer ignore phi double dot term. And then once you do keep phi double dot term, then it starts to behave like a power law. And that's indeed this solution over here. So that's the idea of how inflation actually works. And you're talking about incredible expansion. So in a blitz of a moment, the size as small as the coronavirus would turn into a size of a galaxy. We are talking about really incredible expansion. And you're talking about the exponent being something like 60 or 100. So you're talking about an exponential factor of something like 26 orders of magnitude in a blitz of a moment. And that's the inflation. But while the universe is going through this exponential expansion, then you become very nearsighted because the objects that you think you see in a moment would be far stretched beyond what you can ever see beyond the speed of light in a moment. So basically, only thing you can see in a very small size box. And that box, as I said, is actually microscopic. And if you have a microscopic box, then you know from quantum mechanics, there's an uncertainty principle. So small size box has energy fluctuating all the time. So the empty space would have this incredible fluctuation. And the smaller the box is, you have the larger fluctuation from uncertainty principle. So while the universe is going through this inflationary expansion, which homogenizes the entire universe, because everybody had been together and you're only stretching the same piece of information to the entire space. That's why everything is now homogeneous and isotropic. But while inflation is homogenizing the entire universe, it also creates this fluctuation from quantum uncertainty principle. So in a small space, everything is fluctuating like this. So vacuum is active. So as a result, the quantum fluctuation for this scalar field that is actually causing inflation also fluctuates. Basically, the fluctuation goes like the size of the inverse of the size of the box. And the size of the box is determined by how quickly the universe expands. So everything's determined by this Hubble constant expansion rate of the universe at that moment. So the expansion rate is basically inverse size of the box in the uncertainty principle. So as a result, you have this quantum fluctuation of the scalar field, which is dictated by this inverse size of the box. And this is actually something you can compute in quantum field theory in expanding universe. But if the scalar field fluctuates a little bit from one place to another, then energy density is also slightly higher or lower, depending on which direction this fluctuation goes. So as a result, energy density also fluctuates by the amount given by this expansion rate of the universe. So this quantum fluctuation actually gives you the change in the densities from this rolling down scalar field. And that's the temperature fluctuation George Smoot discovered. And that's the way we actually think about this. So because the inflation was doing this incredible stretch, and because of the uncertainty principle, this field that causes inflation also fluctuated up and down depending on where you are in the universe. So this hotspot is a place where inflation field fluctuated slightly upwards. This blue spot is where the inflation field fluctuated slightly downwards. It's a quantum fluctuation. That's why it's so small at the level 10 to the minus 5. But that's how you actually understand the origin of this fluctuation. So it's almost completely homogeneous because the same piece of information got stretched and covers the entire universe today. So that's the remote islands coming from the same people. Everybody talked to each other first, arranged themselves to have the same temperature, that now got stretched over the entire universe today. But the quantum fluctuation during the inflation gives you tiny ripples of the densities, and that's something you observe in the CMB today. And so this is actually something that George Smoot did using the marching band. And let me actually play this.
I really admired the band, and so when they said we wanted to react to the Big Bang with the guys from your lab, I said, no way, I want the band. Okay, so now I got to tell you what the Big Bang is so you guys can do this before the sun goes down. Okay, so the idea is everything in the early universe was packed together very densely. It may have gone for infinite. We don't have infinite people, so we just have to use what we got. And everything stretched, right? Everything got bigger. And the further away you are, the faster you go. So we're going to want to start at the beginning with everybody packed dense and jostling around and playing high tempo rapid. 1, 2, 3. Then at the mark, everybody moves apart. The people on the outside moving faster than the people on the inside. And there's a little bit of irregular motion, so miss some steps, okay? I know you can do this. Right? And then what happens is you're gonna coalesce together in groups of 6, right? So you have to find 6 buddies, and half of you are gonna form spiral galaxies. 3 people facing one way, 3 the other, and you rotate slowly as you move out, and the other half form elliptical galaxies, which are round blobs that keep moving out. Okay. So now, there's a brass section out there called tubas. They make a really spectacular spiral galaxies, a really big one, like our own galaxy or like Andromeda. So you guys get to be near the middle, and you get to make a really cool, you don't have to run out so fast, but you get to be able to orient where half is facing the other way, and you get to rotate with a sort of twist up. And you're like the centerpiece of this whole thing. Go tubas. Great, guys.
And that's what we talked about in the lecture today. So George is at the center of galaxy, so he's a supermassive black hole, right? And 80% of people here are dark matter. You don't get to see them. And irregular motion, George mentioned, is the quantum fluctuation from inflation. And that led to these clusters of the galaxies at the end of the day. So that's how we now understand the origin of structure in universe today. So I finished my lecture today, but the basic thing we're going to talk about at the beginning of the lecture tomorrow would be this idea that when you use the gravitational wave, which might have emitted when the universe is going through this inflation, because if you stretch the universe at incredible speed, the space itself starts to wobble. That's nothing but the gravitational wave, which we may be able to detect. The gravitational wave can just go through this entire period of dense universe without getting any disturbances because it interacts so weakly. And then that's something we may be able to observe its impact of. Then we can prove the universe is going through this exponential expansion based on observational data. So that's the first topic I'm going to talk about tomorrow. Okay, let me finish today and any questions.
Thank you. So there are any question?
I have questions.
Yeah, go ahead.
Well, first, I just wanted to say that I enjoyed the lecture so much, and I was laughing a lot at
Okay,
most
good,
of your
good.
jokes, but you couldn't hear me, so I just wanted for you to know.
I couldn't hear you.
So the first thing that I wanted to ask, so if I understood correctly, the tiny fluctuations in temperature that you're describing are the size relates to the size of the box when those things were emitted. So if, like you were describing the horizon problem, what I'm trying to think is that you have at first all this tube of baryons and stuff and photons interacting, and at some point it decouples and the photons that are emitted no longer interacts with the thing in the middle. So you can after that see them. So by calculating the size of those fluctuations, you can calculate the size that the universe had at that particular moment when that happened. Mm-hmm. That is correct? Right. It's a good interpretation?
That's basically true. There's a little bit more detail about it though, and I didn't actually explain it fully. So when the scalar field goes up and down a little, how much it can go up and down a little is determined by the size of the box because of the uncertainty principle. Mm-hmm. But how that translates into the fluctuation in energy density today depends a little bit more on the detail of the potential. Mm-hmm.
I see.
Because what you have to do is to compute what is called a gauge invariant quantity, which is a general coordinate invariant quantity. And the numerator is just easy to understand. If you have a potential where field can move just a little bit up or down, the change in the potential is given by V prime times delta phi, and delta phi is given by the size of the box. So that's the numerator. That's easy to understand. Denominator is a little harder to understand. This is actually the rho plus pressure of this field, which happens to be the only general coordinate invariant quantity you can use for normalization. So that depends on basically the kinetic energy of this the scalar field. So this scalar field, of course, depends on the slope of the potential. So everything's determined by the potential alone. You can just go ahead and compute it once you set up a potential energy to actually do the calculation. So everything is fixed by the potential energy. But nonetheless, you do need to compute this ratio to figure out what this fluctuation in energy density is. So that's the only extra step I didn't mention today, but you need to know that.
Okay, I understand. So then, if you go and use what I'm stealing your punchline probably for tomorrow, that the gravitational waves decouple way earlier, so you can see at a much smaller box, and that is for like earlier in time, that means that the fluctuations that you expect to see on the gravitational background will be enormous in comparison to the fluctuations that you see in light because of this argument of the box, or I am not thinking it correctly.
Yeah, actually, that's not the case, it turns out. So that also goes back to this. Sorry, I'm not sharing it. That also goes back to this formula I showed here. So the fluctuation in energy density has this kinetic energy downstairs, which I told you is small because of the friction. So the fact that you have got kinetic energy downstairs is enhancing the fluctuation in energy density. But fluctuation in space-time goes with this scaling of the size of the box itself, so that we expect the fluctuation in gravitational wave is somewhat smaller compared to the fluctuation in energy density as a whole. And that's precisely because of kinetic energy coming in downstairs. So it is a suppressed signal. That's why it's very hard to dig out, but that's something people want to do. And one project that Kosaka mentioned is the Lightbird satellite being planned by the Japanese Space Agency today. And I'm going to talk about that.
That's awesome. I will let all people ask, and thank you so much.
Could you mention about where is a neutrino? There are a lot of students here, so like there is a CMB light and gravitational wave, and then there is a neutrino information, right? Could you mention?
Are you talking about the cosmic background neutrino?
Right, right.
Ah, okay. So yeah, that's right. So if you look at this picture over here again, so light can go only up to this surface. But there may be other probes that can sort of punch through this surface and come straight to us. And neutrino is one example of that. And the neutrinos decoupled from a thermal bath and stopped interacting with it when the universe was only like a second old, as opposed to 330,000 years old. So neutrinos decoupled from the rest of the universe when universe was only a second old, then start to come straight to us. So if you do observe neutrinos that came from there, called cosmic background neutrinos, then you gain information about the state of the universe when it was only a second old. But those neutrinos are incredibly low energies, and neutrino cross-section goes with energy squared. So it turns out that that's a very difficult thing to detect. And so far, there's no experimental confirmation of the cosmic background neutrinos. So that's one of the holy grails in neutrino physics, to detect cosmic background neutrinos so that you can gain information back to the point when the universe was only a second old, but that's still yet to be achieved. And it's one of the dreams we have in the community.
Thanks. There is a question from a student, Vaja. Can you unmute? Yeah.
Yes. Hi. I have one question. So we are going to look at the inflation with gravitational waves, but do we have any other theory except inflations that can explain observed universe without inflation? And if we have, can we distinguish these scenarios with gravitational waves?
Yeah, so the people did try to come up with alternatives to inflation. And I think it's fair to say that's a very difficult thing to do. The inflation, and I'm going to actually talk about this also tomorrow, has an incredible success quantitatively. And to imitate the same level of success without using inflation is a very difficult thing to do. So I think it's fair to say there's no corresponding success with the alternatives. But it didn't stop people from talking about it. For example, people talked about what is called a bouncing cosmology. So maybe universe is undergoing this expansion and collapse many, many times. And then this initial the bounce, people call, is what might have created this initial fluctuation we see in cosmic microwave background. So people do talk about this, and it does lead to a different kind of prediction on gravitational wave, which is the reason that many of them are already excluded by now. So if you think of alternatives, of course, you have to make sure that you draw predictions out of those theories, from the data, and most of the time, they don't work. I think that's a fair summary of the situation.
Thank you very much.
Is this scalar field theory testable? I mean, are we expect to find some imprint of this scalar field theory that you described, for example, in the pattern of the gravitational waves, or how is it testable?
Yeah, so that's a good question too. And the test will be, of course, incredibly indirect, as you can imagine. And depending on what kind of potential you write, then you predict different spectrum of the density fluctuation. So because the inflationary energy keeps changing slowly, but it is changing as a function of time, then the different distance scales will correspond to different height of the potential. and therefore different level of the density fluctuation. So that gives you another quantity called the spectrum index. So it's not completely constant, but the density fluctuation changes a function of the energy scales and distance scales, and that's something you can hope to observe. You can also test if the fluctuation is just a single field or multiple field. In the case of multiple field, you expect the fluctuations not purely Gaussian, but probably something a little bit more complicated. And if you measure many different pixels on the sky, then you can ask the question whether fluctuations is Gaussian or not. And that's another way you test the theory of the scalar field. And also this ratio between the gravitational wave and this density fluctuation is another prediction you make out of the scalar field theory. So you have these couple of handles. But we probably would not be in a situation where you can completely be able to say, this is the theory, and not the other one. And that may not come very easily.
Thank you so much.
Any other questions? Let's see.
Can I ask another one?
Sure.
When you were saying about the fact that you wanted to solve the horizon problem, and you said that exponential growth solves it, why it needs to be exponential growth? Why it cannot be like linear growth? That you just, like with your example with tiny islands, what you need is for them to get away and not to interact with other stuff that might change their language. So you have two ways. You can either move them very, very fast, or you move them and you prevent them from interacting. So why it has to be exponential for it to solve it?
Yeah, that's a very good question too. And people indeed talked about what is called power law inflation. So inflation normally is meant to be exponential, but people did talk about theories of power law inflation. But if you have a power law, then again, you would predict different kind of spectrum of the density fluctuation. And what we need is what is called the nearly scale invariant spectrum. I show you the data tomorrow. So that basically corresponds to the height of the potential being nearly constant for an extended period of time. Power law would change the basically energy density much more quickly. Then you would expect the spectrum of density fluctuation to be quite far away from the scale invariant. And then again, the data doesn't prefer that. So if it is power law, it needs to be very high power so that it would mimic exponential.
Okay, so it's not the fact that they're at a constant temperature, basically constant temperature, that tells you you're in exponential growth. It is that the fluctuations has some pattern that actually on top of that is very, very small, that tells you this will never happen unless you do it super fast.
That's right.
Cool. Awesome. Thank you.